Hello and welcome. This is a science break video for atomic structure and the periodic table. This is for AQA Unit 1 for GCSE chemistry. Timestamps in the description below. Like and subscribe if you can, but other than that, let's get going. The first part of this video is for atoms, elements, compounds and mixtures. Atoms, elements and compounds. Atoms are the smallest part of an element that can exist. For example, if you take the element lithium, here is a block of lithium metal. If you were able to magnify and have a look, you would see that lithium is made of lithium atoms only. Here's another example. This is helium gas. If you were able to take a look at the particles of helium gas, you would see that we have helium atoms only for the element helium. Atoms of each element are shown as symbols. For example, capital O is oxygen, capital L with a lowercase I is lithium, capital H with a lowercase e is helium, and there are about 100 different elements, each with their own separate symbols. The periodic table shows the elements. Here is a small version of the periodic table. We'll be looking at this in a lot of detail throughout this video. Elements can chemically react to make compounds. Sometimes energy is released from or taken into the reaction. Compounds are two or more elements chemically combined in fixed proportions, for example, carbon dioxide or water. If we take a look at carbon dioxide, we can see that for every carbon atom, there are two oxygen atoms. If we take a look at water, we can see that for every two hydrogen atoms, there is one oxygen atom. Here is an example of a chemical reaction. Sodium reacts with chlorine to form sodium chloride. A word equation for this reaction can be written as sodium plus chlorine arrow, which means produces or reacts to give sodium chloride. We can write a formula equation. Na plus Cl2, chlorine gas is written as Cl2, gives us sodium chloride, NaCl. This equation is unbalanced. Formula equations should be balanced. That means the number of each atom on each side of the arrow should be the same. Here is the formula equation again. We can see we have one atom of sodium on the left hand side. So we can write that like this. And we have two atoms of chlorine. Like this. On the product side, we have one Na and one Cl. This is not balanced. What we can do is add another Na on the left hand side. So now the Na on the left, there are two of them. And if we add another NaCl on the right hand side, we can see now that we have two Nas and two Cls. This is now balanced. We can add a big number 2 in front of the Na in the reactant side, and we can add a big number 2 in front of the NaCl on the product side. This is now balanced. Here's one more example. We don't need to keep drawing out the atoms every time. We can just write the atoms as symbols. So we have hydrogen on the left and hydrogen on the right, and oxygen on the left and oxygen on the right. We have two atoms of hydrogen on the left hand side and we have two on the right hand side. So far, so good. But we have two oxygens on the left and only one on the right hand side. So what we can do is add a big 2 in front of the H2O. That changes the numbers around a little bit. The hydrogen is now 4, the oxygen is now 2, and just to finish balancing this, we can add a big 2 in front of the H2, which brings our hydrogens to 4. We can now see that this is balanced. Rules for balancing equations. What we are not allowed to do is add or change the small numbers, so we can't do something like this, move the small 2 to another place. That's not allowed. And we can't add large numbers between the elements. For example, we can't squeeze in a big number 2 in between sodium and chlorine. What we are allowed to do is to add large numbers before an element or a compound like this. If you want more practice for this, you can look up my individual video on the channel on the science break, where I go into this in a little bit more detail. The next part of this video, we are looking at mixtures. These are two or more elements or compounds that are not chemically combined together. Each substance in the mixture keeps its chemical properties, and mixtures can be separated without a chemical reaction. Methods for separating mixtures out include filtration, crystallization, simple distillation, fractional distillation, and chromatography. These are the methods that we need to learn about. Examples of mixtures include salt solution, air, sandy water. There are of course many more, but these are just 3 examples. Let's take a look at filtration. This separates an insoluble solid from a liquid. Here's an example. I've got sandy water, or a mixture of sand and water. Here's my filter funnel, and here's some filter paper. The water is the filtrate, which is separated out from this mixture. This separates mixtures based on the size of particles. Water molecules and other small particles can pass through. Large particles, for example sand, cannot. Crystallization separates a soluble solid from a solvent. That means something that's dissolved in a solvent. Here is how we might do it. The example here is salt solution in an evaporating dish, as you can see in the diagram. Here is a water bath that's used to heat the salt solution, and the water evaporates from the solution. Salt comes out of the solution and forms crystals. So this is how crystallization works. Next, we're going to take a look at simple distillation. The example here is separating ethanol from water. This is a mixture of 2 different liquids. The boiling points are that ethanol has a boiling point of 78 degrees Celsius and water has a boiling point of 100 degrees Celsius. These different boiling points will help us separate out the ethanol from the water. Here is the apparatus for simple distillation. Here's a thermometer so we can monitor the temperature. Here is a condenser. This has cool water coming in and cool water coming out. And we heat the mixture with an electric heater. We would use an electric heater here and not a Bunsen burner because ethanol is very flammable. We heat to 78 degrees. The ethanol evaporates, passes through the condenser, which cools down the vapor, and the vapor condenses. We end up with pure liquid ethanol. Once no more liquid ethanol comes through, we know that we have separated out all of the ethanol from the mixture. Fractional distillation can separate many liquids at the same time, but we'll take a look at that in our paper 2 video. Next is chromatography. This separates inks or pigments from a mixture. This is the apparatus. We have filter paper. We have solvent. In this case, the example of a solvent is water. And we have our ink mixture on a pencil line at the bottom of the filter paper. The solvent, in this case water, soaks up the filter paper. It dissolves the inks, which move up at different speeds through the filter paper, and they separate. Water and inks soak upwards along the filter paper and separate. There is more detail about this in paper 2. Next, we are looking at the development of the model of the atom. Before the discovery of electrons, atoms were thought to be tiny spheres that could not be divided. We then had the discovery of electrons, so the model changed. We have the plum pudding model of atoms. Here we can see that we have electrons embedded in a ball of positive charge. So the red is a ball of positive charge, and the electrons, which are negative, are embedded in that ball of positive. Then we have something called the alpha particle scattering experiment, which changed the model again. This worked a bit like this. We have a very thin layer of gold foil. We have a beam of alpha particles which are fired at the gold foil. Alpha particles are helium nuclei with a charge of 2+. And we found from this experiment that most alpha particles pass straight through the very thin gold foil. Some are deflected in different areas, in different regions, and a small proportion are reflected straight back. This is an example of new experimental evidence leading to a scientific model being replaced. The plum pudding model was replaced. Here we can look at the alpha particle behavior in this experiment and look at the conclusion that was drawn from their behavior. Most pass straight through. The conclusion was that most of the atom is empty space. Some are deflected or reflected. That means the atom has a positively charged center. The fact that only a small number are reflected means that most of the mass and charge is concentrated in the center of the atom. This experiment led to the nuclear model of the atom. The nuclear model was a bit more like this. there is a positively charged nucleus and electrons orbit that nucleus. There's your positive nucleus in that diagram. If we compare that to the plum pudding model, which is something we do have to be able to do, we can see that the plum pudding model is all solid with no empty space, whereas the nuclear model is mostly empty space. For the plum pudding model, the whole atom is a ball of positive charge, whereas in the nuclear model, the positive charge is in the nucleus. The mass of the plum pudding model is spread throughout the atom, whereas in the nuclear model, the mass is concentrated in the nucleus. Electrons are embedded in the ball of positive for the plum pudding model, whereas in the nuclear model, they are in orbit around the nucleus. So there's a comparison that you should be able to do for this chemistry paper. But that wasn't the end of it. We have a scientist named Niels Bohr who adapted the nuclear model to suggest that electrons orbit the nucleus at specific distances. His calculations about this agreed with the experimental observations. So now we have electrons at different distances from the nucleus in shells. We then have the discovery of positively charged particles in the nucleus called protons. And then another scientist, James Chadwick, provided evidence of neutrons in the nucleus. We don't need to know details of how he did that. So then, as a summary, we have the earliest models. We have the plum pudding model. Then we have a series of nuclear models with shells added, the discovery of protons and neutrons, which gives us the modern day model of the atom. Remember, Chadwick discovered neutrons. So now we know atoms are always neutral. They have no overall electric charge, and that's because the number of electrons is always equal to the number of protons in an atom. Almost all of the atom is empty space. Next, we're going to look at the detailed structure of an atom and the relative electrical charges of subatomic particles. Here is the nucleus of an atom. It contains the protons, and it also contains neutrons, shown in green there in my diagram. This is the nucleus that contains the neutrons and the protons. We also have shells around the nucleus, and in the shells, or on the shells, are electrons. There's 2 electrons there in our diagram drawn as crosses. We also need to be aware that the radius of the atom is about 0.1 nanometers. That's 1 times 10 to the minus 10 meters. That's shown there in the diagram above. The radius of the nucleus is about 10,000 times smaller than the radius of the atom. That makes it 1 times 10 to the minus 14 meters. And there it is shown in the diagram. We need to know the subatomic particle, the relative charge and the relative mass, and the location of those subatomic particles. First, we deal with protons, shown as red in my diagram. The relative charge on a proton is +1. The relative mass is just 1. The neutron, shown in green, has a relative charge of 0, or neutral charge, or no charge, and a relative mass of 1 as well. The location of both of these is in the nucleus of the atom. We then have our electrons as shown by crosses. The relative charge on an electron is -1. The relative mass is very small, much smaller than the relative mass of protons and neutrons. It's about 1/2000th of their mass, but we can write very small. The location of those is in the shells of the atom. We should be able to draw an atom from the information given to us in the periodic table. We're going to take the example of sodium. The first thing we do is we notice and realize that the bottom number is the atomic number. This is actually given to you on your periodic table. The top number tells us the number of protons and neutrons. It's called the mass number, but that's the information that it gives us, the number of protons and neutrons. We can write down the 3 letters P-E-N below. That stands for protons, electrons and neutrons. And very simply, the number of protons is taken directly from the periodic table, and that's the number at the bottom of our element there. So we could directly put that into our little diagram below. We have 11 protons. The number of electrons is very simple. We said earlier that the number of electrons is the same as the number of protons. So we can just copy that down to be equal to the number of protons. The number of neutrons is found by subtracting the top number, which is the mass number, from the atomic number. 23 minus 11 gives us 12. That's 12 neutrons. So now we can draw our atom. Here's the nucleus. The number of protons in the nucleus is 11. So I'm not going to draw them out individually. I'm just going to write 11 protons. Then also in the nucleus is the neutrons. So we have 12 neutrons. And then in our shells, we can draw the electrons. We have 11 electrons to draw. So we draw the first shell, and the maximum number of electrons we can draw in the first shell is 2. In the second shell, the maximum number is 8. We need a total of 11, so we've got 2 already. We can add 8 more in pairs. We have a total of 10 so far, and we need 11 electrons, so we need one more. We need one more shell, and we can place our final electron in that shell. It's important to remember that the first shell can carry a maximum of 2 electrons, the second shell a maximum of 8, and the third shell a maximum of 8 as well. We might draw a fourth shell for our slightly bigger elements, but we don't need to worry about maximum numbers for those. We can make sure that we know first 3 shells is maximum 2, maximum 8, maximum 8. Electronic structure. Electrons fill the lowest or innermost available shells in an atom. You can write the electronic structures with numbers or with a diagram. So let's start off with our very first element in the periodic table. This is hydrogen. It has 1 electron in its shell. We can draw that, or we write that as a capital H for hydrogen and the number 1. The next element is helium. This has 2 electrons. So we can write that as He with the number 2. Then we have lithium. Lithium has 3 electrons. It has 3 protons, so we know it has 3 electrons. So we can write that as Li 2, 1. Remember, we can't put any more electrons in the first shell, so we have to move to the next shell. So we write that as 2, 1. Then we have beryllium. You might start seeing a pattern. Beryllium is written as 2, 2. Then we have boron, which is 2, 3. Then we have carbon, 2, 4. Nitrogen, 2, 5. And we can continue like this. Oxygen is next, 2, 6. We have fluorine, which is 2, 7. Neon, which is 2, 8. And we can carry on all the way up to calcium, which has a proton number of 20, therefore 20 electrons. We don't need to know much further than that. So for calcium, the electronic structure is 2882. Next, we need to look at the idea of isotopes. Here are 3 atoms. Each one of these atoms is an atom of hydrogen. You might have noticed there's a slight difference in the nucleus of each. One thing that is the same is that they have the same number of protons. So all of these isotopes have the same number of protons, but they have different number of neutrons. This is what we mean by isotopes. Atoms of the same element that have the same number of protons, but different number of neutrons. They have the same chemical properties, but they have different physical properties. Next, we're going to look at calculating relative atomic mass with given abundance of isotopes. The way that we can calculate this is using this equation or formula here. Unfortunately, you have to remember this, it's not given to you in your exam, but it's the percentage abundance times relative atomic mass of one isotope plus the percentage abundance times the relative atomic mass of another isotope. We add those two together, we divide it by 100, and that gives us the relative atomic mass of our atom. So for example, we have 2 isotopes of chlorine. One has an abundance of 75%, that has a mass number of 35. The other one has an abundance of 25% with a mass number of 37. If we put that into our equation, 75 times 35 plus 25 times 37, add those two together, divide by 100, we have 35.5. This is the relative atomic mass of chlorine, and this is what you will see on your periodic table. Next, we're going to look at the development of the periodic table. Before electrons, protons, and neutrons were discovered, elements were arranged by atomic weight. It was noticed that every 8th element had similar properties. So here is an early version of the periodic table. If I look at this particular column here and move along to the 8th element, you'll find it's sodium, and we can see that they have very similar properties. However, some elements were not in the appropriate places if the order of atomic weights was strictly followed. These 3 elements did not have similar properties to the other elements in the periodic table. Then we have a scientist named Dmitry Mendeleev. His periodic table was a bit more like this. Mendeleev followed atomic weights but left gaps where he thought new elements would be found. There's a gap there where the question mark is seen. In some places he changed the position of elements, for example this one here, so it matched the group more closely. He predicted properties of undiscovered elements. Elements with his predicted properties were eventually found and they filled the gaps. Knowledge of isotopes explained why the order based on atomic weight was not always correct. The periodic table. Here is a larger version of the periodic table. We can see that we have the metals and the non-metals divided by my key there. So on the right hand side are the non-metals, and everything on the left hand side in the lighter grey is the metals. Elements are arranged in order of atomic number. So there's hydrogen there with an atomic number of 1, helium with an atomic number of 2, lithium with 3, beryllium with 4, and so on, arranged in the order of atomic number. We also have elements with similar properties in groups. Here is group 1, here is group 2, group 3, group 4, group 5, group 7, and group 0 at the end there. The rows are called periods. Here is period 1 right at the top. It contains only 2 elements. So that's period 1. Then we have period 2, 3, 4, and so on. The period number tells you the number of shells on the atoms. So elements in period 4 have 4 shells. The middle block of the periodic table, from there to there, contain the transition metals. So that's all the elements in between group 2 and group 3. Elements in the same group have the same number of electrons in their outermost shell. If we take group 1 for example, here is lithium. The electronic structure is 2, 1. You can see there is 1 electron in its outermost shell. Let's take one more example. This is sodium. The electronic structure is 2, 8, 1. You can see again 1 electron in the outermost shell. If we go to group 2, we've got beryllium with an electronic structure of 2, 2. Again, 2 electrons in the outer shell. And one more example, magnesium, 2, 8, 2. Again, 2 electrons in the outermost shell. This means that all the elements in a particular group have similar chemical properties. For example, lithium is in group 1 because it has 1 electron in its outermost shell and has similar chemical properties to other group 1 elements because of that 1 electron in the outermost shell. Let's take a look at metals, non-metals, and group 0, which is the noble gases. Metals on the periodic table. Key thing to remember about metals is that any element that reacts to form positive ions are metals. For example, the metal sodium will form an ion with a charge of +1. Magnesium will form an ion with a charge of +2. We'll look at this in more detail in our video on bonding. Elements that do not form positive ions are the non-metals. So what are the differences? Metals, they are hard and shiny. Non-metals, if they are solid, are dull. Metals have high density. Non-metals have low density. Metals are good conductors of electricity, whereas non-metals are poor conductors of electricity. Metals are good conductors of heat energy, whereas non-metals are poor conductors of heat energy. Metals are malleable, which means they can be bent or hammered into shape, whereas non-metals, if they are solid, are quite brittle. That means they crack. Metals have high melting and boiling points, and non-metals have low melting and boiling points. We've looked at this before, but just to separate out the metals and the non-metals, these are separated like so on the periodic table. Groups in the periodic table. we need to look at three groups. The first one is group 0, the noble gases. These are unreactive and do not easily form molecules. They already have a stable arrangement of electrons. That means they have a full outermost shell. All of them have 8 electrons in the outermost shell, apart from helium, which has 2. Helium has only one shell. It can only hold 2 electrons, so we say that its outermost shell is full. And these are 3 elements from group 0. You can see they all have a full outermost shell, helium with 2 in its outermost shell, and neon and argon with 8 in the outermost shell. Boiling points increase as you go down the group. This is because the atoms become larger as you go down the group. You can see there, I haven't drawn the details of the atoms, but I've just given an overview or an outline of the atom. You can see they get bigger as you go down the group. The reason why the boiling points increase is because the forces of attraction between the atoms become stronger. There I've shown those in red lines, showing a stronger force of attraction between the atoms, and therefore more energy is needed to overcome those forces to separate out those atoms. Therefore the gases have higher boiling points as you go down the group. Remember, it's not the atoms that have a higher boiling point, it's the gases that have the higher boiling points. Next, we're going to take a look at group 1, the alkali metals. Again, here's our periodic table. Group 1 is on the left hand side there. All atoms of the elements in group 1 have 1 electron in the outermost shell, as we have said. This gives them their characteristic properties. We need to know the reactions of lithium, sodium and potassium with oxygen, chlorine and with water. The reactions with oxygen. All react with oxygen to make the metal oxide. In other words, lithium plus oxygen will give us lithium oxide. Here is the balanced formula equation for that. We also have state symbols, S meaning solid, G meaning gas, and S again meaning solid. Sodium plus oxygen gives sodium oxide. Here's the balanced formula equation for that. And potassium plus oxygen gives potassium oxide. There's the balanced formula equation for that one. All of these are white solids that are produced. The reaction with chlorine. Let's take a look at how that works. They all react to make the metal chloride. Lithium plus chlorine gives lithium chloride. There's the balanced formula equation for that. We could take a look at sodium plus chlorine gives sodium chloride. In actual fact, we could take a little animation to see how that works. Here I have a container with chlorine gas inside of it. It's covered by a glass lid so that chlorine can't escape. Here is our example of sodium, and we can take this sodium, we can heat it up using a Bunsen burner, and once we have heated it, we can place it into the jar of chlorine gas. You'll see quite a vigorous chemical reaction. We see flames, a yellow flame, and eventually, once the reaction is finished, we end up with a white solid, which is our sodium chloride. And then finally, potassium plus chlorine gives potassium chloride. And there's the balanced formula equation for that one. Next, the reactions with water. All of them react with water to make the metal hydroxide, which is an alkali, and hydrogen gas. For lithium, it fizzes and bubbles around as hydrogen gas is produced. It floats and moves around on the surface of the water. Your teacher might have demonstrated this for you. If you wanted to see a video of how it all looks, you can look up my video on the groups of the periodic table on the science break, and there it's shown in detail. This is the balanced formula equation. 2Li, which is a solid, reacts with 2H2O, which is a liquid, to produce lithium hydroxide, which is something called aqueous, shown by AQ. This means it's dissolved in water, and hydrogen gas, shown as H2 with a G. This is our lithium hydroxide, which is an alkali. The next one is sodium. The reaction is a bit more vigorous. It fizzes or bubbles more vigorously. It floats around and moves around a bit more on the surface, and it makes a ball shape as it floats around on the surface. This is the balanced formula equation, very similar to the one above, with our sodium hydroxide produced instead of lithium hydroxide as above. Then we have potassium. This is the most violent reaction of all, or the most vigorous reaction of all. It actually ignites to produce a lilac flame. It floats and moves around the water as well, and as we said, it catches fire to burn with a lilac flame. There's the balanced formula equation of the reaction of potassium with water, and our alkali is potassium hydroxide. Next, we're going to take a look at trends in reactivity in group 1. The reactivity increases as you go down group 1. The reactivity of the elements depends on the behavior of outer shell electrons. The reactivity of metal elements depends on losing the outermost electrons. For group 1, the reactivity increases as you go down the group. So here's lithium, here's sodium, and here's potassium. As you go down the group, the outermost electron is further from the nucleus. You can see this by the measurements I've made there. If you look at those three distances, you can see that the distance increases as you go down the group. If the outermost electron is further away from the nucleus, then there is less attraction between the positive nucleus and the electron which is negative. So we can add our positive charges in the nucleus. And we can see that because the distance between the nucleus and the outermost electron is longer, there is less attraction. The electron is lost more easily. Next, we could take a look at the group 7 elements, the halogens. These are over here in group 7. And the halogens all have 7 electrons in the outermost shell of their atoms. They exist as molecules made of pairs of atoms. So we have F2, which is for fluorine. Chlorine is Cl2, bromine is Br2, and iodine is I2. Each atom of our halogen can gain 1 electron when they react with metals. They share 1 pair of electrons when they react with non-metals. Here's our halogens. We can see that the relative molecular mass will increase as you go down the group. The melting point and boiling point increase as you go down the group, and we have to be able to explain why. Molecules get bigger as you go down the group, so here are our molecules. And what happens is we have stronger forces of attraction between the molecules, as shown by those red lines there. That means more energy is needed to separate out these molecules, which means that the melting and boiling point increases as you go down the group. The reactivity of the halogens depends on gaining 1 electron on the outermost shell. Here's fluorine, here's chlorine. The reactivity decreases as you go down the group. This is because the outermost shell is further away from the nucleus. You can see that distance is bigger as you go down the group, so that means there is less attraction for the outer shell electrons. That means an electron is less easily gained. This makes less chance of gaining an electron, so the halogen becomes less reactive as you go down the group. Next, displacement reactions in group 7. A more reactive halogen can displace a less reactive halogen from an aqueous solution of its salt. What does this mean? We can see that if we have a solution of potassium bromide, which is the salt, and we react it with chlorine gas, because chlorine is more reactive than bromine, as you can see in the periodic table, the chlorine can displace the bromide from potassium bromide and become potassium chloride. The bromide will become bromine gas. Another example is potassium bromide reacting with iodine. We can see that iodine is less reactive than bromine in our periodic table. We can see the iodine cannot displace the bromide from the compound. So in that case, there will be no reaction. So potassium bromide plus chlorine gives us potassium chloride plus bromine, as shown by our first example there. Here's the balanced formula equation for that one. Another example is potassium iodide plus chlorine. This would give us potassium chloride plus iodine. There's the balanced formula equation for that one. We can have a go at some examples ourselves, so you can pause here quickly if you like and see what products there are if there is a reaction. Here we have potassium chloride plus bromine, here potassium chloride plus iodine, here potassium bromide plus iodine, and on the other side there are no reactions. So that's pretty much it. AQA, atomic structure and the periodic table for chemistry. Thank you for watching, and I'll see you soon.